Today we're going to look at a method of integration that will allow us to evaluate some expressions that involve a product. So integrals where you've got a function times another function. Alright, so on the topic of product, we're going to begin the development of this formula by considering the product rule, which we know is the derivative of u times v by the product rule is u times dv dx plus v times du dx. And now I'm going to integrate both sides of this equation with respect to x. So I've just copied the expression from above, integrating both sides with respect to x, integrate with respect to x, integrate with respect to x. I will see that the dx's will cancel out. And then we know that the integral of the derivative of u times v would just be u times v equals u integral of u dv plus integral v du. And if we rearrange that expression, we could write it as integral u dv equals uv minus integral v du. And this is the formula for what we call integration by parts, which was established, as you saw, from reversing the product rule. And so what this formula is saying is that if we pick u and v just in the right way, an integral which may be difficult to evaluate directly through normal substitutions that we've already talked about, we may be able to evaluate this integral by evaluating the right-hand side. Since the two sides are equal, evaluating the right-hand side is evaluating the left-hand side. So let's take a look at how to do this. First of all, the first sign that you're dealing perhaps with integration by parts is that you have a product. And the key thing here, as we mentioned, is to make a decision as to what is u and what is dv in your integrand. So I have u, I'm going to have dv. Later I'm going to need to know what du is, which is the derivative of u, and what v is, which is the integral of dv. So what I want to do is I want to pick a u that's easy to differentiate, and I want to pick a dv that's easy to integrate. And it takes a little bit of experience to get used to figuring out what the most suitable u and v might be. But one thing to always look for is if you have an algebraic expression, a polynomial, that's a good thing to make u, because the derivative of x would be, in this case, a constant, so 1 times dx. And dv is the rest of this, so the dx part always goes with the dv. That's sine x. And if we work backwards to what v is, the integral of dv will give us v. Well, the integral of sine we know is negative cosine x. Alright, so we've broken up our integral in terms of u and dv, and now we can apply the formula for integration by parts, which says that the left-hand side is equal to u times v, which is negative x cosine x, minus the integral of v times du, which is negative cosine x dx. Two negatives here are positive. So the whole idea here is that this integral should be simpler to evaluate than the original one was. And we know that the integral of cos is sine. Bring our other piece down. And we're basically finished, but don't forget the constant of integration because it's an indefinite integral. So the derivative of this should be this original expression back again. Alright, here's another example. Again, we have to choose u and we have to choose dv. So again, I'm going to let my u be x squared and my dv the rest of it. I chose u for x squared because the derivative of that is 2x dx. the power is coming down, which is going to be helpful, as you're going to see. The integral of e to the 3x would be 1/3 e to the 3x. So applying my integration by parts formula, the original integral is equal to u times v, 1/3 x squared e to the 3x, minus the integral of v times du, which is 2/3 x e to the 3x dx. Alright, so now we need to look at evaluating this integral. Well, if you look at this integral for a moment, you're going to realize that we can't integrate this unless we do yet another integration by parts. And so I'm going to get ready to do that. I'm just going to move the expression over, rewrite what I have, and while I'm doing that, I'm going to pull out the 2/3 outside of the integral sign. And now I'm going to pick a new u and a new dv. I'm going to let u be x and dv e to the 3x dx. That would make du the derivative of x, which is 1 dx. And going backwards from dv, the integral would make that 1/3 e to the 3x. So my original expression, x squared e to the 3x dx, is what I had already, minus 2/3 the integration by parts formula, which is uv, which is 1/3 x e to the 3x, minus the integral of my new v times du, which is 1/3 e to the 3x dx. So just to simplify and rewrite this, alright, so now we have another integral to try to evaluate, and that one we can evaluate. We use a u substitution. It's a different u I'm talking about. It's going to create an extra 1/3 coming out front. And so we're going to have 2/9 times another 1/3 coming out, 2/27 e to the 3x plus a constant of integration. Okay, we have one last example in which we have a product of two functions, so likely integration by parts is involved. And here the selection for u and v is a little bit more problematic. I could probably go either way on my decision. So I'm going to let u be e to the x and dv be the rest of it. Alright, derivative of e to the x is e to the x. That's nice. The integral of cos is sine x. And so my original integral is u times v minus the integral of v du. Well, notice that this integral we are not able to evaluate directly. We are going to have to use another integration by parts, as we did with the last question. So we're going to create a new u and a new dv. And this time I'm going to use u to be e to the x and dv to be sine x dx, which would make my du e to the x dx. And my v, the integral of sine, would be negative cosine x. Okay, so we're applying our formula here to this section right here. So putting everything together that I have, I forgot a dx up here by the way, equals e to the x sine x minus, okay, my new u times v, which is negative e to the x cosine x, minus the integral of this times this. And so that's going to be negative e to the x cosine x dx. Okay, just rewriting this for clarity and to do a little bit of simplification. We have a negative times two negatives here, so that's another negative. Integral e to the x cosine x dx. And I notice that I'm back to this integral that ironically is what I started with the original question. So things seem to be going around in a circle here, and that's kind of because of the nature of the functions I'm dealing with, sine x, cos, and e to the x. Now notice that this, though, is the same as this. So if I think of this whole big thing as a variable a, and this is minus a, I could bring this integral back over to the left side, and I'd have two integrals of e to the x cosine x, which means that to finish this off, to evaluate this integral, I could divide by 2, and so I get I'm going to factor out the e to the x on the top. What the heck? Sine x plus cosine x all divided by 2 plus a constant of integration.